All right, this is section 7.5 from the Rolf book. It's about independent events. So here's the definition of independent events. Probability of E given F. So F has already happened. This is event E, this is event F. So probability of E given F. So basically F has no effect on E. So that's just the probability of E. E is its own independent thing. So an example of this would be picking a card, right? Card is an independent event. The second independent event would be flipping a coin. So what's the probability of picking a ace, that's a king of hearts, given that you flipped a head and a coin? Well, they're independent events of each other. So the fact that there's a head here has no impact on picking a king. So the event would be flipping a coin, picking a card, right? So the probability of E given F, so something happened with F, does that affect E? No, it doesn't. They're independent. You can switch this around. The probability of F given E is just the probability of F. Also, if you have independent, this formula follows. The probability of E and F is multiplying the two probabilities together. Probability of E times the probability of F, which is in the Venn diagram, the probability of E intersect F in the Venn diagram. So now we're going to see if a couple of Venn diagrams represent independent situations or not. And we're going to use this idea here, multiplying versus just looking at the intersection. So in the first Venn diagram, I'm going to zoom in here so that you can see it better. Refocus. Okay, so in the first diagram, the universe is 100. Here's the first circle, and here's the second circle. There's 20 here, there's 5 here, there is 30 here. That totals 55, which means there's 45 out here. This is event E, this is event F. All right? So the first thing I'm going to say is probability of E, the chance that E happens is 25 things out of 100. So probability of E is 25 out of 100. So I'm trying to test this formula here to see if this works. Times probability of F, well, there's 35 of those. 35 out of 100. Does that equal the probability of the intersection of those two, which would be 5 out of 100? Does this times this equal that? It does not. So this would be no. Those are not equal to each other. So that means this scenario here represents dependent events. Okay, second scenario. So I'm going to do circle, circle, and this time the universe is 165. There's 52 here, there are 8 here, there's 14 here, there are 91 here. This is E, and this is F. All right, so I'm going to do the same thing. Probability of E is 60 out of 165, because there's 60 there, times probability of F is 22 out of 165. Does that equal 8 out of 165? This one here is harder to tell, so I'm going to use the calculator to help me. So I get 60 divided by 165 times 22 divided by 165. And then I'm going to do 8 divided by 165. Whoa! They're the same. So this times this is equal to this. So then it's in, this is an independent situation. It also follows this scenario here. This is like the number of things we did, like with the overlap and all that. So probability of E union F is equal to the probability of E plus the probability of F minus, so if you do E and you do F, that means you've counted that section twice, minus the probability of E intersect F. Okay, so this should be true. Probability of E is 60 things out of 165. Probability of F is 22 things out of 165. The intersection is 8 things, 8 out of 165. So that times that times, or that plus that is 82 minus 8 would be 74. So it'd be 74 out of 165. That's, now the question is, does the union, this plus that, does that equal 74? Well, that and that is 60 plus 14. Yep, it's 74, equals 74 out of 165. So it matches. So that formula holds too when you have independent events. All right, so there's that. So independent probability of E given F. Let's do the ring question here. The other thing that you get into is mutually exclusive. What is mutually exclusive? Mutually exclusive looks like this. You have E and you have F. There's no overlap between the two things. Mutually exclusive. Okay, so mutually exclusive means there's no overlap between the two things. So one of the rings is diamond and emerald. So the first one is D and E. The next ring is D and R. The next one is ruby and emerald. The next one is pearls. Okay, so are the events E and F mutually exclusive? So that would be E is diamond, F is ruby. Diamond and ruby. Well, diamond and ruby is that ring. So no, they're not mutually exclusive. There's overlap. Are the events independent? Okay, so E has a diamond. Okay, so has a diamond would be 2 rings out of the 4 rings. So having a diamond, probability of diamond is 1/2 times probability of ruby. Okay, so ruby is 2 rings again, so it's 2 out of 4 or 1/2. Does that equal probability of diamond and ruby? Diamond and ruby is the intersection of those, diamond and ruby. So diamond and ruby is just this one ring, 1 out of 4. So is 1/2 times 1/2 equal to 1/4? Yes, it is. 1/2 times 1/2 is equal to 1/4. So are those independent events? Yes, they're independent events, but they're not mutually exclusive. Now I'm going to take us to a page in the book that I read through in class, and it talks about the difference between mutually exclusive and independent, and how those two things can be those things can get mixed up. It's the example number 9 in the book. So it's on page 573, and I like this question, and I'm going to relate it back to something that I have right now, or it's relatable to something that happened recently in my life. So it says, Nikki and Alice are 2 students at the university who do not know each other and have no contact with each other. So they choose classes, right? So that should be independent because they don't know each other. They just make independent decisions. They're independent people. In such a case, it seems reasonable that Nikki's decision to take art history or not has no influence over whether Alice takes art history or not. We say that the events Nikki takes art history and Alice takes art history are independent because the probability that one of them takes the course has no influence on the probability that the other ones. So they're independent events, just like flipping the coin and picking a card, right? They're independent of each other. On the other hand, both could take the course. So the events are not mutually exclusive. To be mutually exclusive, the occurrence of one event must exclude the possibility of the other occurring. So they could end up in the same class, but they would be, but they didn't make that decision dependent on each other. They just accidentally ended up in the same class. So they made the decision independently. It's an independent event, but it's not mutually exclusive because the two girls can be in the same class. Under different circumstances, when Nikki and Alice are roommates, now they're roommates, so they could influence each other, or they could not influence each other. Maybe they just decided to be in the art history class. It seems reasonable to think that Nikki takes art history or not, or might or not might influence whether or not Alice takes it. That is, the events takes art history and takes art history might be dependent, might be. But even if they're roommates, their decisions might be independent. So we need information on the probability of each decision before we can say. Even if their decisions are dependent, the events are not mutually exclusive because both of them take art history. So this is my example. My personal example with this is, there's Mr. Jackie personally. So my personal example of this, there, look straight into the camera. Okay, my personal example of this is with Mrs. Baker. Mrs. Baker and I know each other. We've known each other for a long time. She's a former student. We both have the same car. Now you would think that we talked about it and we have the same car. No, we arrived at the same car independently, even though we know each other. So it's like the roommates that ended up in the same class, but they didn't really talk to each other. It's like, hey, you should take this class, right? So we ended up with the same car. We made that decision independently, but it's not mutually exclusive because we have the same car. It overlaps. So we have overlap in our lives. Mrs. Baker and I also have overlap with the fact that we are both Homo sapiens, right? We're both human beings. We both teach math. We both have the same car. And today was a special thing because we both had we both had Twisted X boots on. So we had the same type of shoe on today. So more overlap between the two. So things can be independent, but not necessarily mutually exclusive. So that's kind of the difference between the two. Mutually exclusive cannot have the overlap. They have to be two separate sets. All right, so enough about this. And stop. Enjoy the problems.